The other notation is big omega notation. So big omega notation, it is provide an asymptotic lower bound. Actually, the big O notation provides the upper bound of the algorithm. It provides the upper bounds of the algorithm. We can define the big O notation, the big omega notation. A function f of n is big omega of g of n if there exists a constant c and n naught is the value of positive constant, such that f of n is greater than or equal to c times g of n for all n greater than n naught. So this is the formal definition of big omega notation. For example, if f of n is n squared, then f of n is big of n squared. You can say this one. In simple term, f of n which equal to big of g of n means that the growth rate of f of n is greater than or equal to g of n. So actually, we can prove f of n square is f of n big of n square, how it comes. So simply we can do that just like in the previous example, as we do in the big O notation. F of n which equal to n square, right? So to prove this one, big of n square, to find big of n square, so f of n greater or equal to c times g of n, right? C times g of n. So n square greater than or equal to c times g of n. So we can add here any function that should be greater, less than these f of n functions or equal to. We can add equal to. So let's try n square greater or equal to 1 times n square, right? 1 times n square. So n square greater or equal to 1 times n square. So this one is when the value of n is what? When the value of n is 1. When the value of n is 1. So n square is greater or equal to 1 times n square. That is true. So this will be the possible answer. So this one is what? This one is c, the value of c, and this one is the value of d. The value of g of n, the value of g of n. So which means f of n which equal to omega of g of n. So f of n which equal to the value of g of n is n square. So f of n which equal to omega of n square. So we can prove just like this one. So which means any function less than n square is the possible answer for this one. The possible answer in case of omega notations. And the third one is theta notation. So a function f of n is belong to the set of theta of g of n if there exists a positive constant c1 and c2 such that it can be sandwiched between c1 g of n and c2 g of n for the sufficiently large value of n. So when we see the formal definition, if a function f of n is theta of g of n if there is both big of g of n and omega of g of n. In the other word, there is a constant c1 and c2 as well as k greater than 0, such that C1 J of n less or equal to f of n less or equal to C2 J of n for all n greater than or equal to k. If f of n is equal to theta of J of n, then J of n is an asymptotically tight bound for the function f of n. Now let's consider the previous example, or let's take this simple example, or simple f of n which equal to 2n plus 1. Then let's prove f of n which equal to theta of theta of n. So to prove this one, f of n which equal to 2n plus 1, right? 2n plus 1. So it should be tight bound between less or equal to C2 times J of n. And also, let me rewrite again. So in the definition, C1 times J of n less or equal to f of n less or equal to C2 times J of n. So in the place of this function, or C1 times J of n, in this one, we should add the function that is less or equal to f of n only, less or equal to f of n. So to do this, we can simply 1n, 1 times n only, less or equal to f of n is 2n plus 1, 2n plus 1, less or equal to, we should write the function which is greater than this one, So 2n plus 5n, we can consider this one. So 1n less or equal to 2n plus 1 less or equal to 7n. So this is true when the value of n is greater than or equal to 1. So greater than or equal to 1. So this is a possible answer. So the value of C1 will be 1. This one is C1. And this can be C2. Or we can simply, this one is C2, and this one is J of n, right? This one is J of n, and this one is J of n, and this one is f of n. So actually, instead of 7, we can replace with 3 also. It is true. When we replace 3, when we replace the value of C2 is 6, it is true. When we replace 5, it is true. And also when we replace 4, it's also true. And or when we replace 3, it's also true, or it is greater than this function. So we can make a 3n plus, 3n is the value of C2 of C2 of J of n. So it is here we will put the largest value and the largest function of f of n. So f of n which equal to theta of J of n. So which equal to, what is the value of J of n? It is n, right? So simply we can put theta of J of n is equal to theta of n. So f of n which equal to theta of J of n. So this is all about today's lesson. Thank you for watching. till 1. See you later.